In this video, we'll be discussing about the inverse process of differentiation, that is called integration in calculus. Now, what exactly is integration? Let's first define it, and then we will learn the mathematical techniques for getting the job done. So let's say we start with a function y equals capital F of x. That's a function. Now what we do is we differentiate it. So we carry out differentiation on this function, and we end up with dy by dx equals small fx. So this was the original function, this is the function we get after differentiation. Now what we do is, now this is pretty much what we may call notation. Dy can now be written as small fx times dx. And now what we do is we carry out a process called integration. Now for that we have a symbol, it's this symbol here, dy integrated, and also on the right hand side we carry out the same process, basic concept of mathematics, that in an equation, if we carry out the same process on both sides, the equation remains valid. And once we do this integration on both sides of this equation, we are back with the original function. So once we get from here to here, the process is called differentiation. And when you get from when you go from here to here, the process is called integration. So this is what integration really is all about. Now that is one way of describing integration, but not the only way of describing it. Let me give you another way of looking at it. And to do that, let's imagine a cricket match to be going on, and let's say we have a very aggressive batsman. Let's say we have Virender Sehwag batting, and we define a function. Let's say this function y is Virender Sehwag's score. Now this score, of course, would be a function of x, and x is the number of balls that he has faced. So x is the number of balls faced by Virender Sehwag, and y is his score. Now when the bowler delivers one ball, the number of balls faced changes by 1, and that's sort of your dx in here. So a change in x every time one ball is delivered would be dx, and that would be 1, and dy would be the change in the score y, and dy could be anything from 0 to 6 on a particular ball. Now change in Virender Sehwag's score, that is, could be anything from 0 to 6. Now dy by dx would be the rate of scoring per ball, and that function is small fx. Now let's take this simple example. The bowler comes, delivers one ball, and Virender Sehwag hits this first ball for a 4. Now for this first ball, dx would be 1, x, the total number of balls faced, would also be 1, and dy is 4 since he's scored a 4 on this, and his score y is also 4. Now the second ball comes in, he again hits a 4, and so this time dx is 1 dy is 4, x is now 2, and y is now 8. Y, the score, is now 8. And then the next ball comes and he hits it for a 4 again. And this time dx was 1, dy is 4, x is now 3, and y is now 12. So these balls keep coming and he keeps hitting every ball for a 4. What you must have noticed already is that when we keep adding all the values of dy, we get y, the score. So when we keep adding all the changes in y, we end up with y. And what do we end up with when we integrate dy? When we integrate dy, we get here. So when we integrate dy, we get y. And when we do a summation of dy, we add all the values of dy. Again, we get y. So in that sense, integration is a summation. So when we do a summation of dy, we get y. When we integrate dy, we get y. So they are the same thing. So integration is a summation of dy, which in turn tells us that integration is also a summation of fx dx. Because if we are doing a summation on the left hand side of the equation, the right hand side must also be a summation, because we carry out the same process on both sides of an equation. So integration is not just the inverse process of differentiation, but it is also a summation, right? So integration is also a summation of dy or of fx dx. So integration is actually these two things. Now, depending on the kind of application we are doing, we might end up using one of the two interpretations, often both. Now, since integration is described as an inverse process of differentiation, the formulae for integration are also the inverse of the formulae for differentiation. So, the basic formulae that you will need to remember for integration are all the inverse of the formulae on differentiation. So, if x to the power n dx is integrated, we will be doing everything that's the opposite of what we would do in differentiation. So in differentiation, the power would decrease by 1. Here it would increase by 1. In differentiation, we would multiply by the power. Now here we will divide by the increased power and get your integral. That's the formula now. Now in integration, there is one little rule that we follow. We have to add on our behalf an unknown constant c. Now where does this come from? Quite easily understood actually, but with an example. Suppose we had y equal to x cube plus 5. Now we had this function with us a few years ago, and we differentiated it and we got dy by dx equal to 3x squared. The 5 disappears in the process of differentiation. Now when we integrate this, we have dy equal to 3x squared dx, and we are integrating this. Now we need to integrate because we've already forgotten what the original function was. So we now are not really aware of what the original function was. And since we are not aware of the original function, when we integrate and we get, of course, if this was x cube was differentiated, we got 3x squared. So when we integrate, we get back to x cube plus, now we know we are doing it right now, so we remember there was a constant 5, but if we do not have the original function, or we've forgotten the original function, there is no way for us to recall what the constant was. So we need to add an unknown constant on our behalf. So we assume there might have been a constant, and therefore we add it. The value of the constant may be 0 or non-zero, whatever, but we do add this constant. So this kind of integration always requires the addition of an unknown constant, and that is why this type of integration is called indefinite integration, because we do not know the definite value of the function on this side of the equation. So this was the first formula. Of course, there is a condition here. This n should not be equal to -1. Now I'll get back to the reason for this. N should not be equal to -1. Reason for that comes when I take up the next formula, and that says 1 upon x dx equals, now you will recall 1 upon x was the derivative of natural log of x. So on integrating 1 by x, we should get natural log of x. Now this actually is x to the power -1. And so when we have x to the power -1, we apply this result and not this one. And so it becomes pretty obvious now why the condition was applied. The third formula, when you integrate cos x dx, you will recall that cos was the derivative of sine, so we get sine x plus c. Sine x dx integrated gives us minus cos x plus c. Then we have sec square x dx. Now sec square x was the derivative of tan x, so integration gives us the inverse result. And the sixth one, if you remember, I gave you 6 formulae, main ones for differentiation. I'm giving you the inverse formulae for integration. And so now with e to the power x dx integrated gives you e to the power x plus c. So with e to the power x, whether integrate or differentiate, it doesn't change, it remains pretty much the same. So this is the basic concept, the basic definition of integration, and some basic formulae on integration. Now we are not always going to get such straightforward results to work with. I mean, what will happen is, in mathematics you don't just have 6 types of functions, you can have more complex ones, and often we need to handle those. There's an infinite variety of functions that you might end up integrating in mathematics, but in physics we can manage pretty much with some more addition to this list of 6 formulae. So therefore I will now give you some of those techniques we'll be using for the slightly more complex kind of functions. Integration is actually a sort of a modeling case. What you do is build up models for the process of integration for different kinds of functions, and based on those models, whenever you see a function that resembles one of your models, you work with that model and arrive at a result. Now, as I said, some of the techniques that you'll be using for slightly more complex functions. So you can call these rules, formulae, results, whatever. The first thing you need to understand is that when you're integrating and you have a constant times a function in this manner, then the constant comes out and you simply integrate the function. So for example, you had 3x square dx. When you integrate, the 3 came out. I mean, this was the example we were just discussing. So 3 comes out and we now have x squared dx, and on integration x to the power 2. Now when we integrate, what's done is we increase the power by 1, so 2 plus 1 becomes 3, and we divide by the increased power and add an unknown constant. So 3 cancels and you have x cubed plus c. The next thing you need to understand is when you are integrating a sum of two functions. Then the integral is simply the sum of the two integrals. So f1x dx plus f2x dx. For example, if you are integrating sin x plus x squared dx, you simply integrate them separately. Sin x dx plus x squared dx integrated, and this gives us minus cos x plus x cubed by 3 plus an unknown constant c. Another example here. Now remember one thing before proceeding further, that in integration we do not quite have a product rule or a quotient rule or a chain rule, but there are certain techniques, and I'll be giving you those in the following cases. The next technique we use in integration is when you have an integration where the numerator is the derivative of the denominator. Whenever the numerator is a derivative of the denominator, the final result is natural log of the denominator plus the unknown constant c. Let's take a simple example. Cos x by sin x dx. When you integrate, what do you get? Easily noticeable here that the numerator is a derivative of the denominator, and so on integrating we will end up with natural log of the denominator, that's sin x, plus the unknown constant c. So simple technique here. Next sort of model that you need to remember, and that is, if you have a function fx dx, and when you integrate this function you get, let's say, a function capital Fx plus a constant c. Now if in this function in place of x you have f of function of a is a constant, ax plus b dx. Now in place of x the function has ax plus b. Here on integrating we will get capital F, the same function, On integrating this function, we got capital Fx. On integrating the same function again, we get capital F of, in place of x, we had ax plus b. But one little change, you divide this by a. Now this is a model that mathematicians have developed. It's quite easy to reason this out, and I leave it for you to figure out on your own why it is the way it is. So all you need to do is, if in place of x you have ax plus b, a and b being constants, the integral is the same function with x replaced by ax plus b. The only change that you make is that you divide by the coefficient of x, that is a over here, and of course you add an unknown constant c. So for example, if you were to integrate cos 3x plus 4 dx, then the integration will give you, now cos when integrated gives sine, cos x dx when integrated gives sine x, but in place of x we have 3x plus 4, but the change you make is you divide the whole thing by a, and a here is 3, and add this unknown constant c. So that's this model, or this rule you can say. And then one more, and this one's fairly simple again. You have a function fx and it is raised to the power n, and then you have f prime x dx. So you have a function raised to the power n, and then you have a derivative of the same function times dx. The integral now will be fx, this function, raised to the power n plus 1 by n plus 1 plus c. Now let me give you a simple example of this. Sin x whole cube into cos x dx. What you have now is a function sin x raised to the power 3 times cos x, its derivative, into dx. The integral now gives us sin x to the power 4, we increase the power by 1 and divide by the increased power, plus the constant c. So this is the simple set of rules that you can use in integrating the different kinds of functions. Now, as I said, in mathematics, the variety of functions that you will need to integrate will be pretty much infinite. But in physics, with what we have learned so far, you can pretty much manage a very, very large majority of applications, very, very large majority of questions that you can possibly get in your exams. Getting very, very close, I think now, to say about almost 100% of the questions in academic exams, and maybe 95-98% of the questions that you can get with the competitive exams. So whatever additional we need to learn, we will learn as and when required, rather than stressing ourselves at this initial stage of our learning. So this is indefinite integration that we have learned so far. Moving now on to what's called definite integration. Now, what's definite integration? Well, the integration we've learned so far invariably involves the addition of an unknown constant. With definite integration, the unknown constant isn't required. Now, why this is happening the way it is happening is, we were kind of calculating Virender Sehwag's score, but we did not know from how manyth ball to how manyth ball. Like we were not aware. Okay, we have to calculate his score from the 5th ball to the 20th ball, or from the 1st ball to the 50th ball. So we were not aware of the requirement exactly, and therefore we were adding an unknown constant. But suppose we are told that we have to calculate Sehwag's score, or the number of runs that he makes after the 25th ball all the way up to the 60th or 50th ball, let's say. So from the after 25th ball up to the 50th ball, how many runs does Virender Sehwag make? Now let's make a simplistic assumption that on this particular day Virender Sehwag was in particularly good form and he was hitting every ball for 4. So from 25th, at the end of 25th ball, he would be at 100. And then the next 25 balls, again if he's hitting a 4 every ball, he is now at 200 at the end of 50 balls. So how many runs does he make after the 25th ball and up to the 50th ball? Well, we just take the difference in his scores at 100 ball mark and subtract from there his score at I think I made a mess of it. We subtract his score after the 50 ball mark. Big mess. We take his score at the end of 50 balls, and from that score we subtract his score after 25 balls, and that gives us 200 minus 100, that's 100 runs scored. So that's kind of what indefinite integration is. We will not need to add a constant because we will know exactly from where to where we are doing the summation. So, you know, if this function integrated gives us capital Fx plus c in the indefinite integration process, you know, this was indefinite integration. What will happen in definite integration is that we are doing a summation, we are doing an integration, but we are doing this summation from x equal to a. Now in the Sehwag example, a is 25 balls, to x equal to b, and in the Sehwag example b is 50, and this equals, now this was the score, remember, so this equals the score after 50 balls minus the score after 25 balls, and there is no constant here. We know this precisely, exactly how many runs he made from the 25th ball up to the 50th ball. So this is definite integration. How the process is implemented will become a little more clear if we take a simple example. Let's say we are integrating x square dx, and these limits of integration are from x equal to, let's say, 0 all the way up to x equal to 3. Now when you integrate x square dx, it's the formula number 1 that I gave you. Integration gives you x to the power, increase the power by 1, divide by that increased power, and then add an unknown constant c, but then we won't need to do that here. We are implementing definite integration, unknown constants are not there. X equal to 0 to x equal to 3. Now this function here is your capital Fx, and this is x equal to b, this is x equal to a. Now in this capital Fx, what we'll do is we'll substitute x by 3, and that gives us f of b. So x equal to 3 is substituted here, minus f at x equal to a. Now a here happens to be 0, this is capital Fx. So we calculate the value of this capital Fx at x equal to 0, and we now have 27 by 3, that's 9, and the job done. So this is definite integration. With definite integration, there are no unknown constants, and we get a definite numerical value at the end of the process. Now, just like differentiation did, integration too has a geometric meaning, and we'll now be exploring that. Geometrical meaning of integration. Now, as in differentiation, the geometrical meaning comes from graphs of functions. So let's say we have, this is the y-axis, x-axis, and we draw a graph of a function. Now this is a graph of y equals fx, that's our function. We have drawn the graph of this y equals fx, and we are now looking for the geometrical meaning of an integral. Now what integral? Let's say over here, this is x equal to a, and this is x equal to b. And we are looking for a geometrical meaning of this integral. Which integral? Well, the integral we are looking at is fx, this function, times dx, integrated from x equal to a to x equal to b. This is what we are looking for. Geometrically, what does this represent on the graph? Now, at some value of x, let's say this value here, this is x somewhere, this would be fx, f of x. So this height here is f of x, that's the y, and this is x. Now what's dx? Easy to recall that dx is a small change in x. So this is your change in x, dx. And this is the new value of fx. So this height here is fx, and this width here is dx. When you multiply fx with dx, you get the area of this strip here. So I've drawn this strip. The area of this strip is fx times dx. Now what you're going to do during integration is you're going to do a summation of fx dx. Now fx dx is this area, and you're doing a summation of fx dx from x equal to a to x equal to b. In doing this, you will be doing a summation of all such areas of strips. Let's say, for example, you start over here, there is a strip here, this strip, then the next strip, and then the next strip, and then the next strip, and you're doing a summation of the areas of all the strips. Now if you do a summation of the areas of all the strips, what do you end up with? What you end up with is the entire area under the graph from x equal to a to x equal to b. So we are going to get the area enclosed between this vertical line drawn at x equal to a, this vertical line drawn at x equal to b, and the function, the graph of the function, and the x-axis. So these are the boundaries, and in these boundaries we get the entire area. So geometrically this equals the area under the graph of y equal to fx between the limits x equal to a and x equal to b. Of course, the area is limited by this vertical line at x equal to b and x equal to a, and the x-axis and the graph of the function. So we get that area here. Now, to be more certain of this, let's take up a simple example. Now we'll take an example which will confirm for you that the process is correct. Now we very well know that the graph of y equal to x will be a straight line. Now remember, y equals mx plus c is the equation of a straight line. Here m is 1, so the slope is 1, and when the slope is 1, that means tan theta is 1. When tan theta is 1, theta must be 45 degrees, so this line makes an angle of 45 degrees with the x-axis. What about the y-intercept? Well, over here the y-intercept is 0, so this straight line actually makes a 45 degree angle with the x-axis. So this is x, this is y. This straight line makes a 45 degree angle with the x-axis, and its y-intercept is 0. So it passes through 0 over here like this, right? So this is the graph. This was y. I made a bit of a mess. Now we are interested in calculating the area under this graph from x equal to 0 all the way up to, say, x equal to 4. Now I have selected this simple case where the equation is that of a straight line because now we end up with a triangle, and with a triangle we can always calculate the area. Now what's the area under the triangle? Or let me shade the area so that we know exactly what we are talking about. It's this shaded area that we are discussing. It is this area that we are talking about. So how much is this area? It's a triangle, so it's half times the base. That's 4 from here to here. This is 4. The value of y when x is 4 will also be 4 because y equals x. So 4 again, and you have 8 square units. That's the area. So we already know the area. So since we already know the area, if we now run an integration process and calculate the area, we should get this answer, and if we do, we will be fairly certain that the process is correct. The interpretation we've arrived at is a correct one. So let's see if integration lets us arrive at the same result. The function here is x, then we multiply it with dx, fx dx, and integrate from x equal to 0 to x equal to 4. Now when you integrate, this was x to the power 1, integration leads to x squared by 2, and you're integrating from x equal to 0 to x equal to 4, and this gives us 4 square by 2 minus 0 square by 2, and that's 16 by 2, that's 8 square units, which is the answer that we were expecting anyway. Now this set of videos, the 3 videos that I have done on introductory calculus for students who are beginning to learn physics, these are very important videos, and perhaps if you're a beginner with physics, you need to go through these a fair number of times so that the ideas are all internalized. The largest majority of students struggle with physics for the simple reason that they fail to develop a reasonably good understanding of physics at the beginning. And in India, in our country here, there is no teaching of calculus even for those who take up mathematics as a subject at the initial stage. Calculus comes up in curriculum about a year after they have started studying physics, whereas the applications of calculus in physics start right away. So we cannot wait for a year or a year and a half to learn calculus, because learning of physics makes it essential. In mathematics, you will learn this in far greater detail, but then as I said earlier, our purpose was to learn mathematics up to learn this calculus up to a level that enables us to learn physics, and that purpose is pretty much served in these 3 videos. Perhaps you will need to go through them a number of times before these ideas are internalized, and you can try out some problem solving, some examples from your sources, books that you have. Try out some questions and get a little more proficiency going in this. Thanks very much.